Alrighty, so now that it's turned 8:05, we can get started. To all of those in the presentation, welcome. This is Shadow Crystal's first, what we're calling STEMinar. It's a series of STEM-related, especially with a leaning on physics, webinars that we're doing for the high school demographic and especially FRC students. So our first seminar is on DC motor dynamics with an emphasis on FRC. My name is Tristan Lord. Online you might know me as John PID. I'm the former control lead of FRC 8726. I served 3 years on that team. Oop, hello there. That's another member. We're just getting into the introduction for the member who just joined. And I am presently working with my co-founders to found a new team, FRC 11755 Shadow Crystal. So let's get into it. Before I get into the details of the presentation, I would just like to emphasize that I will be pausing for questions rather frequently, and if you ever wish to express your question, feel free to, whenever I pause between slides, just unmute and say your case. So it's not an especially formal meeting, so let's just get into it. So I believe it's worth defining our scope when it comes to a presentation like this, because when it comes to motor dynamics, it's a very broad topic. There are a lot of types of motors, and not all of them are used in FRC, so what we're going to do is focus our scope onto specifically FRC applications of DC motor dynamics. So essentially that would mean your Neo Vortexes, your Neo 2.0s, your Kraken X60s, all modern FRC motors. The physics do also apply to brushed motors, for those of you who might know what a brush motor is. But in FRC, all you need to know is that the motors you use are what are called brushless outrunner DC motors. And we'll get into that, what that means more in a bit. It's also worth noting that we're not going to be handling the exact equations. We're not going to be handling numbers. We're going to be handling proportions, relations between values, when one thing doubles, another thing doubles, proportionalities, something equals some constant times something else. Equations like that are what we'll be leaning on pretty heavily to do our derivations here, because it's the easiest way of explaining FRC motor dynamics in a brief time frame. So before we get into the educational portion, although this is rather educational, excuse me, let me admit one more person. All right, hello. We're just getting into the first question slide. So for those of you who are very into FRC, you're probably aware of what this is. This is a swerve module. This smaller motor spins the wheel rotationally. This larger motor drives it across the ground. You'll have 4 of these on a robot to make a full drivetrain. To those of you who might know it already, I'd like you to either in the chat or unmute to describe the formula of the feed-forward equation for an FRC motor, and then either in the chat or to yourself, consider if you're confident that you could predict how this module would move based on your knowledge of motor dynamics as they are now. Does anyone happen to know the feed-forward equation already? And if you don't, that's totally fine as well. So, what our goal is today is in fact to understand this equation. This is known as the feed-forward equation. And in isolation, a powered DC motor without any external forces applied onto it will move according to this equation. If you've ever been in the WPI lib documentation, if you're a software kid, then you'll know this as the feed-forward equation if you've looked at the control theory section. And it is vital to being able to operate a mechanism accurately. We're going to be dissecting what each term means, how the equation can be derived, and how you can use it to effectively control your mechanisms. And no matter how good your CAD is, this is the reason that we do control theory in FRC. A lot of times you'll just let SysID handle it, or let Krakens handle it, or let the latest and greatest Motion Magic handle it. But the reason you want to understand things at the physics level is because it helps you to optimize and tune and think flexibly and, in general, adapt your control algorithms to new external forces. I always go back to this example. Back during 2025 Reefscape, for like younger students, you had to basically put PVC pipes on coat hangers of sorts, and you had to position your mechanisms within like centimeter precision to actually effectively score the PVC pipes onto the coat hangers. And if you didn't, that could be the difference between going to Worlds and not. So a strong grip over the feed-forward equation allows you to really effectively optimize your control algorithms and ensure that your robot can succeed. Now, the way we get to the feed-forward equation is first by considering the forces on a DC motor. And by doing so, we can derive the feed-forward equation, which is pretty cool. Those forces are going to be friction and what's known as the net Lorentz force produced by the current within the motor's windings. It is totally okay if you don't know what Lorentz force is. We will get into that. Before I go any further, does anybody have any questions? Okay, cool. So, to begin, we're just going to start with the simplest of the forces, that's friction. So this is what's known as the rotor of a brushless DC outrunner motor. This is a dissection of the components within a DC outrunner motor. In some capacity, all of the motors in FRC have these parts. You might think, oh, well, if the rotor is... Okay, perhaps I've jumped the gun a bit. So, to explain, the stator has what's known as the copper windings of the motor. These are the copper wires that are coiled into many winded rings, if you will, looped around what's known as the stator, and they are powered in a process called commutation, which we won't get into today, that essentially allows the rotor to accelerate in one rotational direction. The rotor in an outrunner motor sits on top of the stator, engulfs it, and rotates around it. So if you've ever seen let's say, a neo-vortex spin, that's your rotor spinning on top of your stator. You see the whole thing spin. You might think that a Kraken isn't an outrunner motor, but what a Kraken really is an outrunner motor with an outer protective shell. So if you were to take this outer shell off, you would actually see that it's very similar to a neo-vortex on the inside. So in this rotor, you have permanent magnets which interact with the electromagnets in the stator to create a torque, and again, we'll explain how that works soon. As this rotor rotates, it will experience a approximately constant force of friction against the bearings. Now, this force is going to be very small when you're just using a pure motor because bearings are going to minimize that friction pretty heavily. However, as you have like an actual mechanism with some weight to it, or potentially use a significant gearbox or heavy gear ratio, that friction is going to become a lot more significant. And the force of friction is going to be equivalent to some constant times the negative sign of your velocity. What that means is that the force of friction will always be in the direction which opposes your movement. So let's say your motor is spinning clockwise, your friction is going to be pushing counterclockwise. And just as a reference, throughout this slideshow you might see constant or K as a very common coefficient. That's just a stand-in for some number. Not all K's are the same. You will see multiple K's in an equation. They are not all the same value. They're just a stand-in for some number which is dependent on the properties of the individual mechanism. Now, to effectively understand Lorentz force, it's important to understand Ohm's law. Some of you might already have a background understanding of Ohm's law, but it is worth reviewing for this context. Now, Ohm's law is given as the following. V equals IR. V is representative of a voltage, I is representative of current, and R is representative of circuit resistance. I personally find that the best analogy for understanding this is to think of a wire like a river, and each electron like a piece of salmon. Okay? Hear me out. Current can be thought of as the amount of electrons that travel past a certain point in the river per second. Voltage can be thought of as the pressure with which these salmon are demanded to swim. So when voltage is higher, current is going to increase because the electrons will be moving faster and more of them will be passing past one point in the river per second. Resistance can be thought of as how hard it is for the salmon to push through the river. So let's say that your material is more resistive to current. That means that these salmon are going to have to push harder to maintain the same amount of current. You're going to have a higher voltage. Resistance is dependent on the length of your wire. So if your wire is longer, it's going to be harder for the electrons to get through. It's like a longer swim. There are also different materials. So like let's say you had to make a salmon swim through honey or syrup. It's going to be harder than if it's swimming through water. That's why we use like copper and silver when we're doing wires. It's because they're highly conductive. Does that all make sense? To anyone, if anyone in the audience has questions, ask them now because we're going to get to the dense magnetism stuff's starting pretty soon. Okay, very good. So, moving on. The Lorentz force. FB is the notation that we will be using to describe the Lorentz force. And what you need to understand is this diagram. Now, this is a diagram of a brushed DC motor. The only difference you need to know for now, you're never going to use brushed DC motors in FRC unless it's like some old parts for like a demo bot or something like that. All you really need to know for now is that in a brushed DC motor, the windings rotate while the permanent magnets stay at rest. So what you're seeing here is a diagram of a very, very simplistic brushed DC motor. However, the physics for the Lorentz force are the exact same between the two types of motors, so you don't have to worry. What we're seeing here is a current labeled as I flowing through the windings this way. Can y'all see my cursor okay? The laser pointer that I have? Okay, cool. Now, these are two sides of permanent magnets. You've got your north pole and your south pole, and they have a magnetic field going this way. That's your field vector B in blue. The way the Lorentz force works is that when you have a current flowing one way and a perpendicular magnetic field component, 90 degrees offset, the Lorentz force is equal to the product of those times the length of the wire that the current is flowing. So for example, this part of the wire actually doesn't experience a Lorentz force at all because this magnetic field component is parallel. So it won't experience any because there is no perpendicular component. At least in this diagram. And yeah, that's the Lorentz force in a nutshell. So what I'd like you to consider is, you've reviewed Ohm's law, V equals IR. You know Lorentz force. Lorentz force equals current times wire length times magnetic field strength. Now, this is a diagram of a Rev Neo motor belted to a linear actuator. So essentially, if you've ever played Minecraft, you've ever seen a piston, that's what this is. It just moves up and down in a straight direction. So let's say you're programming this linear actuator and you call set voltage of 6 volts on this motor, and then in a different trial, you call set voltage 12. How would the Lorentz force from the 12 volt output differ from the 6 volt output? By what factor, perhaps? Does anyone possibly know? You can type your answer in chat as well. You don't have to be correct. Even a guess is okay. That's correct. Very well done. Larry in the chat said by a factor of 2. That is correct. So, the reason for this is such. Lorentz force equal to current times length times magnetic field component. Your Ohm's law is given as V equals IR. So, you can rewrite this expression to say current is equal to voltage over resistance. And what you have to recognize in this situation is that your wire length is constant, your circuit resistance is constant, and your perpendicular magnetic field component is, for all intents and purposes, approximately constant, because if you go back to the diagram right here, you have a relatively full set of circular permanent magnets, so the field will remain relatively constant. Oh, excuse me, I skipped a bit too far. So, when your B, your L, and your R are all constant, you can think of things in terms of proportionalities. So if your V over R equals I, you can substitute that in for I in your Lorentz force equation. And so you get 3 constants times your voltage, or in other words, some constant times voltage, is equivalent to your Lorentz force. And that is why your Lorentz force in a DC motor is proportional to your voltage. Because when you apply a certain voltage, that voltage is proportional to the amount of current you apply, and so your Lorentz force becomes proportional to your voltage. Does that make sense? Okay, very good. But there's a little bit more to it. See, when you have a certain voltage, there are forces at play that are just more than the controller output. When you call set voltage of some number on your motor controller, you're not going to always get that amount of volts, because there is a counteractive, what's known as electromotive force, which is just another word for voltage, which works in the opposite direction to the voltage that you try to apply with your motor controller as your motor gets up to speed. If there wasn't this counteractive force, the motor would just accelerate forever. But that's not what happens in reality. You apply a certain voltage with your controller, and the motor reaches a peak speed, an equilibrium. Why does it do that? It's due to an electromotive force called back EMF. And to understand back EMF, you need to at least have a cursory understanding of what's called magnetic flux. Magnetic flux is defined relative to a certain enclosed area, and it is equivalent to the parallel component of the magnetic field through the area times the magnitude of the area itself. So for example, if these magnetic field lines were traveling straight down, the flux would be zero, because no amount of field lines are traveling parallel through the area. However, the flux would be maximal if this magnetic field was pointing straight horizontal across the screen, because the angle would be at its 0 and cosine would be 1, if you've taken trigonometry yet, which I'm assuming most of you have. If you haven't, that's fine. All you need to understand is that as the magnetic field lines become more and more straight with regards to the area, the flux is going to go up. If you've taken like any vector physics yet, or vector algebra, you'll know that this is the dot product. Now, that magnetic flux formula, you see the symbol here? This is called phi. And what you'll see here is that phi appears again. For those of you who haven't taken calculus yet, this is just this is a bit of notation which is representative of the rate of change of magnetic flux with respect to time. So, this is what's known as Faraday's law of induction. And it is in play when you have an enclosed winding or wire with a defined area like this. The area of this winding is just the area of the square it creates. So, this is a diagram, it's somewhat reminiscent of the previous diagram, but this is actually a diagram of a generator. This is a very basic fundamental generator. Again, two magnets with a magnetic field going this way, and a mechanical crank. When you turn this crank, what happens? Well, consider the magnetic flux through the winding as it is on the diagram. It's parallel to the... Oh, we got a new joining. That's one of my co-founders. Okay, resuming. So, as you turn this crank, excuse me, as you turn this crank, the amount of magnetic field which is actually going through the winding increases. So for example, if you were to turn it 90 degrees from where it is on screen right now, it would be almost perfectly perpendicular to the area vectors. So you would get maximum flux. Whereas as it is now, it is almost perfectly parallel and you're going to get virtually no flux. If you were to turn this crank faster, excuse me, almost jumped the gun a little bit. So before I get into that, Faraday's law of induction, do pardon me. So this symbol here is equivalent to the EMF induced. That's your back EMF. It is equal to the number of coils, or in this case windings, times the rate of change of your magnetic flux. As the magnets in your brushless DC motor rotor rotate, the windings in the stator experience this changing magnetic flux, similar to what you see in the generator here. The only difference is that the magnets are moving, not the windings. So you're going to get a change in magnetic flux, and you're going to get some amount of back EMF. And it goes backwards because of this negative sign right here. Now, before we go any farther, this is also time for questions, but I'm just going to propose this question first. What factors do you think might influence the rate of change of magnetic flux through the windings in a motor? What do you think might make the rate of change faster? What can you do to the motor? What could the motor be doing that would make magnetic flux change happen at a faster rate? I'll give you guys like 30 seconds for this. All right, all those answers are absolutely correct. So when you get obviously stronger motors, like Tihan said, that's going to lead to a greater change in the magnetic flux. But in this case, when we're dealing with permanent magnets, when you set it to a higher voltage, as Ethan said, it's going to spin at a faster speed, and when it reaches equilibrium, what that means is when you turn this, so I'm just going to go back to this slide. When you turn this crank faster, this winding rotates more rapidly. And so you're going to get this change between no flux and maximum flux happening much more quickly. So yes, speed is proportional to the rate of change of flux, meaning that back EMF is proportional to the rate of change of, back EMF is proportional to speed. Now, it's worth noting that back EMF opposes electromotive force exhibited by the controller of your motor because of Lenz's law. In other words, an induced EMF, like the one in back EMF, will oppose the change in flux that caused it. So, for example, the speed of your motor is inducing the change in flux, so the back EMF is going to try to slow down your motor to counteract that change in flux. So, with all that in mind, we can get into the math-heavy stuff. So, this is your net Lorentz force. The sigma symbol just means net, sum, the sum of all the forces. So that's going to be equal to some constant times the sum of your electromotive forces. Your sum of electromotive forces is equal to the controller output, which we're just going to call V, that's the voltage that you put when you say set voltage in code, plus epsilon, which is the back EMF. Back EMF, in turn, is some constant times your velocity, because back EMF is proportional to your velocity. And then, finally, you can expand this into two terms. Your net Lorentz force is equal to some constant times your controller output minus some constant times your motor's velocity. Does that make sense? Do we have any questions? Alrighty then, we'll keep going. So, now we're going to get to the actual modeling of the system. We have Newton's second law. The net force on the system is equal to mass times acceleration. You'll learn this in physics if you haven't taken it already. So you have your force of friction, your representation of back EMF, we'll just call this Fe, and your Lorentz force due to your controller output. And you sum them to get your net force, which is equivalent to Ma. This is the sum of the forces on a rotor of a isolated DC motor. Now, I'm going to ask you one last question. Actually, that's a lie. I think I have one more after this. Does this look familiar? I'm going to give you guys 1 minute. It's about to turn 8:29. I'll give you guys till 8:30. Toy with this equation on paper for a little bit and see what you can reproduce. If you find anything that might be interesting, let me know in the chat. All right, to those of you in the chat who figured it out, very, very good. This is a rearranged format of the feed-forward equation. So what you'll find is ma equals all these forces. You add these two terms to the side of the equation with ma, and then you divide out the k coefficient on controller output, and you are left with the feed-forward equation. And this is the basis for why the feed-forward equation works. You don't get told this as often as you should, in my opinion. The WPI lib docs don't provide for this, because this derivation is why the feed-forward equation works, because it is just derived from the net forces exhibited on a motor. And once you realize that, each one of these terms starts to click, and you really start to understand why the feed-forward equation what it is, and how to actually solve for these constants and apply it to your control algorithms. So, we're going to now break down for the rest of this slot presentation, I think we're making fairly decent time, how to use each feed-forward term. So, just to begin, V is your controller output voltage. We'll get to how to actually use this in combination with PID control in a moment. This term here, Ks times the sign of your velocity, is the voltage required to negate friction. Kv times your motor's velocity is the voltage required to negate back EMF at a given speed. If you were to apply these two terms to a... Hello there. And as a side note, all of these slides will be posted on our website, shadowcrystal.org, and provided that this recording goes okay, which it's still recording, it should be good, will be end up on my YouTube channel as well. That's John PID Talks Bots, but we will, that's for later. So, going back into the presentation, and then, so if you were to apply Ks, your Ks term and your Kv term to your motor, what you would find is that slowly but surely, you would reach the velocity that you set here, because you would enter an equilibrium at which the friction is being counteracted exactly, and your back EMF is being counteracted exactly. And that really goes to show the value of the feed-forward equation to maintaining a state, especially in velocity controllers. If any of you have had to program a flywheel or to try to hold a motor at a certain speed for like a shooter or something, you need to use the feed-forward equation to counteract the forces on a motor which try to keep it from moving. And then lastly, you have this Ka times acceleration term, which essentially represents the amount of voltage you need to apply to exhibit a certain acceleration on the motor, provided that you are at your desired velocity and that friction is being compensated for. Does that all make sense? All right, very good. So, how do you use it? Well, you set up feed-forward control by first defining your constraints. Your constants. Those are your Kv, your Ks, and your Ka. And then, whenever you are doing control operation in code, you plug in your desired state into the feed-forward equation. Some might wonder, why don't you plug in your actual state? Because you're trying to counteract a certain force, why don't you counteract it as it is right now? The reason for that is that it helps to keep the system stable. See, if your Kv that you estimate is actually higher than it is in reality, then, then what you'll find is, if you apply it for a certain velocity, you're going to have more voltage than you need to counteract back EMF at that speed. So your motor is going to accelerate. And then, once that happens and your velocity increases, what's going to happen? Your feed-forward output is also going to increase. So it's almost this greenhouse runoff effect, which destabilizes the subsystem and keeps it from maintaining its state effectively, which is effectively the point of feed-forward. So you don't want that. Then, as you can sort of see in this block diagram, your feed-forward controller has this output, that's your controller voltage V, and it is added to your feedback controller's output, that's going to be your PID controller. and that is inputted into your system. So it's going to be your feed forward output plus your PID output. Now, one last question. Think about ways that you could potentially empirically derive estimations for these three constants. And then consider the value of these three constants across different mechanisms. Perhaps consider the last mechanism you've catted or the last mechanism you saw in a robot reveal. And think about how feed-forward might be applied. Feel free to share this in the chat. We've got 20 minutes before this meet has to end because it's got that 60-minute limit, but we should be good. Okay, moving forward. So, first we're going to consider the friction term since it's the simplest. So, as I previously stated, the significance of the friction term grows as you add more gear reductions or your mechanism gets heavier and you have more moving parts, because your friction is going to increase. Typically, you'll estimate Ks very, in its most granular form, by just applying a certain incremented voltage, like on 8726, we would just do 0.01 volt increments until your mechanism just barely starts to move. And that's going to be your Ks. You also want to make sure that your Ks implementations account for the sign of the velocity term, since that means that your friction will change direction. There are some exceptional cases where you can actually use friction to your benefit and not actually compensate for it. I recall in my district, in 2025, I was discussing with a very successful team, and I was like very new to control theory then, and it was also interesting and wonderful. It still is, but more fascinating than perhaps it might be now. And I was talking with them, and I was like, surely they must have some intricate control algorithm to handle their multi-jointed arm with a wrist. No. They had a 250-to-1 gearbox, and it was held up entirely by friction. So, sometimes you don't need a big fancy control algorithm as much as you just need a big gearbox. And in that sense, you can use friction to your benefit. Back EMF. This is your back EMF term. And the significance of back EMF is pretty large in most mechanisms. Excuse me. Velocity control algorithms, as I previously touched on, are completely dependent on a stable KV in order to hold a certain velocity. I took this image of Citrus Circuits' 2019 shooter from FRCdesign.org. If you can't tell, this is a little flywheel drum right here that gets up to speed to fire projectiles out this way. And in order to hold the speed well, you need this steady state feed-forward term in order to consistently counteract back EMF in a way that your feedback controller can't, because your feedback controller is dedicated to keeping error at a minimum, not holding a certain state. Now, your position control algorithms, these are your elevators and arms and whatnot, aren't necessarily reliant on KV, but they still benefit from it because of its applications in motion profiling. Now, motion profiling is unfortunately out of the scope of this lecture. There's fairly good documentation on it on WPILib and on other websites because it's a very common procedure. Now, in KV can be approximated through like a manual tuning method, for example, just using your motion profile and tuning different values of KV to see what does best. Or you could set a known voltage, especially with a velocity-controlled mechanism, and then measure your steady-state speed. So what you can do is you can treat this component of the equation almost like a y equals mx plus b plot. This is your m, this is your x, this could be your y, and this could be your b, where you apply a certain voltage once you've discovered your Ks, and wait for it to reach a steady state. At that point, acceleration is 0, so this term no longer applies. And then you know your velocity, you know your voltage, you know your friction, so you can just solve for your kV. Does that all make sense? Very good. So, moving forward, your acceleration term. This one, let's just say, if your mechanism is cooked, this isn't why. It's both difficult to approximate because your velocity and your friction terms are going to be slightly hard to also get at the same time, and it also has minimal use cases. It's nice to have when you're optimizing a motion profile. My understanding is that CTRE motion magic does require you to input a Ka value, but it is difficult to get one that's very precise. To accurately use it, you can try using a calculator like Recalc, which will take the parameters of your system and output estimates. You can also try, as a certain member in the chat, I want to say it was Ethan, touched on, it was Ethan, to use a system identification tool like SysID or Advantage Scope to try to estimate your Ka value. You can also attempt manual tuning on top of otherwise complete motion profiles to just see what works best. Many times, if your mechanism especially isn't ideal, you will get a negative Ka. That's okay. It just goes to show that your Ka isn't necessarily the largest factor contributing to your system, because a negative Ka is just not true. It's never going to be true. But sometimes this ID will say that if your perhaps identification algorithm wasn't perfect or your mechanism is unideal. Now, the previous slides cover what's known as a simple motor feed-forward. That's when you just have, like I've been saying, a motor in isolation. But what happens when you have external forces? Take this pivot. This is an intake. I want to say this might be 1678's. No, this was a crescendo intake. I could be wrong. So you have this pivot pivoting about this axis, rotating up and down to intake. I believe these were foam rings called notes, if memory serves correctly. And what you'll find, if you do the math, is that the extra feed-forward term is equal to kg times cosine theta, where theta is your angle from being parallel with the ground. Why is this? How do you derive this? Well, that's what we're going to do. So, the way you do this is you just consider how this would work for Newton's second law. Set up your Newton's second law equation with your net force being equal to ma, and consider how the force of gravity can be modeled. Well, when your pivot, the center of mass of your pivot, is all the way 90 degrees from being parallel with the ground, like this, all of the weight of your arm is resting on top of the pivot. So the motor doesn't have to do any work to actually hold the arm up. Whereas when the center of mass is parallel with the floor, none of the gravity is actually being supported by the pivot. So you're going to have to do a lot more work. And that's why this cosine theta term comes in, because when your angle is 0 and you're parallel with the ground, you're going to have a maximal gravity. Oh, call-on's in 15 minutes. That's okay. We're making good time. And when your angle is 90, you're going to have no force of gravity at all. So once you have your net force equation set up, what you can do is, again, rearrange it to be the feed-forward form. And what you'll find is that your cosine theta just propagates through, and you're going to get this kg times cosine theta term. You can then try to estimate the empirical value of kg. Usually what this works as is, in some capacity, raising the arm to a known angle relative to its center of mass, and then incrementing, again, your voltage that you apply until the arm can just barely hold itself up without any help. That's going to be your kg. And then once you have that, your velocity is going to be approximately 0, so these terms won't apply. So you're going to have some angle theta, some voltage, divide your voltage by your cosine theta, that's going to be your kg. And this method of figuring out how to model external forces translates to other mechanisms. So if you have an elevator, your gravity is going to be constant. That's just going to be some k. you simplify into the feed-forward form, then it's just going to be kg times nothing. It's just going to be a constant on its own. Does that make sense? Very cool. So, that is the end of the presentation as we have today. We will be introducing and promoting a soon-to-be held seminar on the aerodynamics of model rocketry, and this will be involving like center of mass, center of pressure, an emphasis more on Newtonian mechanics rather than AP physics, electricity, and magnetism. Again, I'd like to thank you all for coming. You've been a wonderful audience.